это все выложить. Так, да, все, запись пошла. Ну, тогда, значит, еще раз, да, я рад приветствовать всех на нашем семинаре Центр квантовых технологий. Мы открываем новый сезон с семинара Павла Секатского Limits of Quantum Metrology under Markovian Noise. Пожалуйста.
Да, спасибо за приглашение. На самом деле я присоединился в этот канал из-за confinement, ну, из-за карантина, да, потому что сидели дома, делать было нечего. Мне Алексей сказал, что идет такой семинар, вот стал смотреть по вторникам иногда. Поэтому я тут оказался, теперь буду вам рассказывать. Я буду рассказывать по-английски, потому что я как бы вообще всю науку изучал на французском и на английском, и мне очень сложно по-русски термины некоторые, я не знаю просто. Хорошо?
Конечно.
All right, then. Before I actually go to the main topic, I would like to give you a very brief appetizer of. Oh, that doesn't work now. Okay, of something else we were doing. So I actually asked Stas whether you would be more interested about quantum metrology or about device-independent things, right? So he said quantum metrology would probably be more interesting for the majority of people. But I just put on one slide on device-independent analysis of quantum experiments. So just to tell you very briefly what we are doing. So it's actually kind of related to Bell violation, right? So typically, you know, in an experiment, you have like black boxes, right? So preparation of the state, some evolution, the measurement settings, and you observe some probability distribution, which relates the controls, the inputs to the outputs. And on the other hand, you have like a mathematical model, a quantum physical model of the setup, right? Where the state you think is described by some vector on a Hilbert space, you know, associated to the degrees of freedom you are using in the lab, and evolution and measurements, etc. And the usual thing is really you have a model and you try to predict the observations, right? So the probabilities. But basically, device-independent analysis is trying to go the other way around. So can you just from the probabilities make some conclusions about the quantum model of the experiment you're running? So an example, you know, is a Bell violation of Bell inequality, right? It actually proves that your state is entangled, regardless of what the Hilbert space on which the states live, right? Or what the measurement POMs are. There is no separable state which can explain these correlations, right? So this is one example. But in fact, you can go much more in details. And for example, self-testing allows you to really identify very precisely which describes your elements of a quantum model. So for example, something we did recently, so we derived such protocols for control phase gates, also CNOT, quantum memories, right? So really you run an experiment where from the measurement data, you can conclude that the device which you were using at some part actually was described by a CNOT, for example, right? Up to some equivalence transformations, typically local basis choices. Yes, and another important research which we're doing in this direction is actually QKD. So you can do the same thing, but if you're not interested by really identifying the model of your setup, the quantum model which describes your setup, but sometimes you're just interested to bound the information, for example, available to an eavesdropper, right? Which is precisely the goal in QKD. Then you can also do it in a device-independent way. This is known as device-independent quantum key distribution. Yeah? So we also had some recent contributions on this. So I think it's very interesting, actually, this area. It's not very much known to the broad audience. Yeah? So really the fact that in many cases correlations can identify a state uniquely, it's self-testing. It's quite fundamentally interesting, I would say. So I hope you get interested and read a bit more. Right, but now let's go to the quantum sensing part. So it's a bit a long talk, right? A bit longer than usual, let's say 45 minutes. So yeah, I heard you need a plan then if it's longer than 20 minutes. So here's a plan. I'll actually first give a very general tutorial on parameter estimation, fish information, not really related to my own research, and then present some results on my own, right? Of my own. So it will be 50-50, I would say. Yes. So then let's start, right? So yeah, you know, so I start with this citation of Immanuel Kant from Kritika Чистого разума. Basically, it's a banality, you can say, right? That a cause cannot produce all its consequences instantly. But this is also, in quantum sensing, I would say, we are trying to to quantify the statement, actually, right? So what we are trying to do is precisely to see how fast a cause can produce its consequences, and how, from measuring the consequences, we can learn something about the cause, I would say. This is kind of the general picture we have here. And if you want to be a bit more precise, really the general question I'm going to try to answer during this talk is the following. So Now here we have everything we need. So basically we have some quantum probe, which is just a quantum system, which interacts with the environment, yes? Now in this environment, there is something which we'll call the signal. For example, the strength of a magnetic field, right, in a lab, which we would like to learn, but also on top of it, there is some noise. So the environment will also put some noise on the probe, which we don't care about in principle, but it will harm the estimation, right? So it will make it more difficult to estimate the signal in the first place. And then in the most general scenario, what we can do is we can also have a computer, or actually a quantum computer on site, which doesn't really interact with the environment, but which can apply controls on the state of the probe, right? So we have like a continuous loop like this, where we can at the same time like either read out the state of the probe or do any unitary control or whatsoever control. And so we let it run for some time, such a protocol, right? And at the end, we want to learn actually from all the readouts we have during this evolution, or also the final measurement, right, which we do at time t. We want to learn about the signal, right? So for example, typical example is the strength of a magnetic field. So we want to estimate the parameter B, which is encoded there, right? So really our general goal will be to say so very it's a difficult task. We have to say what is the best, what is the best probe state, what is the best control strategy, which allows you to do this. So this is really a general question, what we want to answer. Now we will really start with the tutorial, so I will go to very basic things and see how we formalize this question, right? So here is an example of an estimation scenario. Yes, so we have some parameter, which is, for example, here's the temperature of the chicken. Yes, which is really physically there, right? So let's say chicken is at some temperature, and then it interacts with the probe. In this case, it's a thermometer, and then we read out the signal from the probe, right? So we just look on the thermometer and get some number, but maybe this number is noisy, yeah? So I don't know if the hands are shaky or something like this. Then formally what we have here is actually the observed result x. So what we read out is a random variable, right? And this random variable actually comes with a parametric model. So if you know the physics of our chicken well, then we know exactly how the distribution of the results, the probability to observe a certain x, depends on the value of the parameter. Yes? So this is precisely this parametric model. This is a central quantity here. Px given b. So, and the question, of course, is how to estimate b. So given x, how to go back to b, yeah? And how to say if an estimation scheme is good or bad, right? So this already, basically, I would say there are two ways to see this problem. The first one is just the Bayesian one. So basically, if you have a prior distribution of b, so I know from some general reasoning that the b is distributed according to some prior distribution, p0 of b, then of course what I can do is just I use the Bayes rule. So because I know the parametric model, I know px of b, I can actually revert the dependence, right, and get the conditional distribution of b, knowing that I have observed x. Yes, so this will be now my updated knowledge. So once I do the measurement, I update my probability distribution, and now probably it's more narrow. So I actually have extracted some information on b, right? This is clear, I hope. Or maybe if you have some questions here. In general, just don't hesitate to interrupt me. I think we are in a small committee, so it will be very nice if something isn't clear.
Okay, everything clear.
Everything is clear, great. So this is sort of, there's a Bayesian analysis for this, right? You really have always this beliefs, and you update them every time. Now, another way is more like Fisher way. Actually, the guy you see here is Ronald Fisher on the picture. And there is more to stay with random variables. So now, given that x is a random variable, I can define a function of x. We will call it b hat of x, right? Which is just a function of x. And this is let's say it's an estimator. So it's an estimator if the value of b is close to the true value of the field, right? So if the estimator, so for example, an unbiased estimator, this is a function for which the expected value, whose expected value actually coincides with the true value of the parameter, right? So in other words, if I repeat the same scenario many times, then on average, I will observe the estimator's average will correspond to the true value of the parameter, which I want to estimate, yes? Now you can also say how precise it estimates, and for this we can define the mean squared error. This is just simply the average, the expected deviation of the estimator from the true value, right? Okay, so now this is a different kind of, it's actually a different mathematical formalism in the sense that to define these estimators and B, we don't need to talk about the prior at all, right? Because the variance of an estimator is well defined even at a fixed B. Even if for a given true value, we can still talk about the variance of estimator, because it's not the variance of the true parameter, it's actually the variance of a random variable, which is B hat. Yes? So far, so good, I guess. So we will now dig a bit more in this fish information thing and the estimators. So first, maybe we start with a simple example of coin flipping and see what we get there. So now let's take, so this Swiss francs. Yes, we say we just flip it many times. So we flip the coin and the coin is biased. Right, the coin is biased and the probability to observe a head is given by h, some parameter we want to learn. And obviously then the probability to get the tail is 1 minus h. And let's say we make now n tosses of the coin, and actually what we want to estimate is h. So if n is large, you know well that the binomial distribution of the total probability to observe n tails and m heads is basically well approximated by a Gaussian, which has a mean, right? So here t bar is now the frequency of heads, let's say, right? So if t bar is the frequency of heads, a random variable, then its mean is precisely given by h, yes? And the variance is given by this thing I plot here, right? So h times 1 minus h. I mean, this is just Gaussian approximation of a binomial distribution. So now if I look at this, an obvious thing is that an obvious estimator for h is precisely t bar, the frequencies of heads, right? So in other words, saying something trivial, we can use the frequency of heads as an estimator for the bias of the coin, for the probability of heads, yes? So now fixing this estimator, let's look on its mean squared error. And precisely its mean squared error is given by, because it's a Gaussian, now it's a Gaussian variable, this mean squared error for large n, and it's precisely given by the variance sigma square, right? So you see that it's this quantity here, h times 1 minus h divided by n. Which so far it's all trivial, but now we can just rewrite it a bit in a different form, right? I just take the same formula, I write it in this way. So 1 divided by something, and then we rewrite it again by this way, where there is a derivative of h with respect to itself appearing, the h prime. And actually, if you write it like this, then what you see appearing here, this function in the brackets, it's called the fish information of the estimator t bar, right? So in other words, it's the fish information of the probability distribution associated to the frequency. So we'll come to it later. This is just an example where you see it appearing naturally from very basic reasoning. So kind of this formula you see here, which tells you that the mean squared error of the estimator will be related to its fish information, is actually quite general, and we will come to this later. So it doesn't only apply to this coin example, but it's completely general in fact, and it's called the Cramer-Roo bound or Cramer-Roo theorem. Yes. So let's look a bit more, there's a bit more details on this thing. So now what we have again, right, is remember we have this parametric model. This parametric model, Px given B, gives us the probability to observe some value x at a fixed value of a parameter B, right? So now mathematically, right, what does this object describe? Well, it's actually a curve on the simplex of probability distributions, right? Do you agree with this? Because what we have is just for each fixed B, for each fixed true value of the parameter, we have a distribution of outcomes. So this point on the triangle, on the simplex of probability distribution. Yes. And now when we change B, well, we'll simply have some trajectory onto this probability distributions, right? So I'm saying something trivial here, right? Basically, the parametric model, it just describes a curve in the space of probability distribution depending on the parameter. Yes, this is clear, I hope. We can also write it now going from probability distributions to vectors, right? Just to find the square root, we can also define it as a curve on a positive quadrant of an hypersphere here, right, on the right. Now, obviously, somehow the estimation of B, how well I can estimate B, should be related to how fast I move on this curve. So how fast my outcome probabilities change when I change B, right? This is very intuitive. Right? So if by changing B a lot, I will change the probability of outcome a lot, then it means that I will detect very easily this change of the parameter. So it will be good for estimation. But then the question, of course, is how to quantify this change. And so what the fish information offers is precisely kind of a formula, right? So far we just take it up as a formal definition. as a formula which allows you to compute the speed of evolution, right? So this fish information of P at B, this actually gives us how fast the probability changes when we change B at a given B, right? So now I'll just give you a list of equivalent definitions, which you can pick the one you like, because maybe some of them look more intuitive, right? So one other way to do it is just, instead of starting with a fish, we can start with a fidelity, which is a measure of kind of how close probability distributions are, all right? And then just expand it to the first order around B, right? So it will be, so in other words, fish information also tells you how fast the fidelity drops when you move along the curves, right? So how fast the probability distributions become different. Similarly, if you go to the curve here, we can just, you see this is even nicer maybe. So the fish information tells us, given this curve on a sphere, how fast the angle of my vector increases. Yes? So when I change B, I move away from a probability from the vector R to a vector R plus B plus dB, right? And then if I look on the substitutability of this angle, which A is here, really the angle, the R cos of the overlap, then the fish information is the square of the speed, okay? And then there is also a definition with the score function, which is equivalent, yes. And so I hope this gives a very nice kind of geometrical picture of what actually fish information of a associated to a random variable is, right? Does it? So it's really just, if you draw these probabilities of this outcomes, you can really see it as some geometrical speed of evolution of the probability with respect to the parameter, right? And well, why it's also important, because you have the Cramer-Roo bound, which we already mentioned, but I'll just put it formally. So the Cramer-Roo bound tells us that for any unbiased estimator, the mean squared error of the estimator is lower bounded by 1 over the fish information. So in other words, you cannot estimate the parameter well if the fish information is low, right? So the bigger is the fish information, the smaller is the limit on your error. Okay? And basically what you see here is just I copied it from a lecture from last semester. So this is actually a formal proof of the Cramer-Roo bound. So it's a very simple statement, in fact. You can, I mean, we're not going to prove it now, but it's really nothing difficult. Okay? Do you have questions on this? So the idea here is that we relate a speed of evolution of probability distributions to how well it can estimate the parameter, right? So this mean squared error. So this is Cramer-Roo bound is somehow central to understand why the fish information is important quantifier of this. Yes?
That's clear.
Okay, now we have to, so this was classical, right? So far just probability distributions, right? And random variables. Now I have to go to the quantum case. The quantum case is not very different, but of course it is different. So here the difference is that, well, if you want to describe a quantum scenario where the probe interacts with the chicken and so on, so we will have then first the initial state of our probe, the thermometer, then we will have some interaction, which is kind of a parametric evolution, right? So an evolution which depends on the parameter and on time. Then once the probe interacts with the chicken, we get the final state of the probe, which is again the quantum state, depending on T and B. And finally, if we choose a measurement, how to read out, how to measure the probe, then at this point we get back to the classical thing, right? We get back to this parametric model, the probability of the outcome given B. Well, here it's omega, but never mind, right? So it's kind of, so at the moment where I fix the measurement and everything, I'm back to the classical case. But of course, before it, there are different steps. So I have to choose a state, I have to choose maybe the channel to some extent. Yes, so, but the goal is again the same. So once you have this probability of the outcome given the parameter, we want to estimate the parameter, right? So let's see what changes here, right? So now if before our parametric model was actually a curve in the space of probability distributions of measurement outcomes, yes, now if we fix the initial state and we fix the parametric evolution, so this channel, so then the final kind of the parametric model now is quantum. So instead it's a curve in the space of possible states, right? So it's really this curve rho B. Now instead of having probability distributions of outcomes, we really have kind of a curve in the state of possible final states. Yes. So because of course final state will be different depending on the parameter value. So this is the kind of the basic object we work with now in this curve in the state of density matrices. Okay. And maybe one thing we can ask now is, because we want to talk about quantum sensing, quantum metrology. So is what do we mean by quantum? Yes. So in particular, when we talk about sensing with quantum probes, I mean, you know, in some sense, everything is quantum, right? So what do we mean by this? So to do this, actually, what we need is kind of separate all the possible resources we can have into quantum resources and classical resources. And once we have it, we can talk about like quantum advantage as the advantage in the sensing, which you only get with quantum resources, generally quantum resources, right? The most simple case is just suppose the probe is composed of many systems, yeah, n systems here. Then we can talk about initially preparing probe in an entangled state, right? So preparing all these qubits in an entangled state. Then we'll talk about kind of quantum resources for sensing, or in separable state. Then we'll talk about classical resources, right? So in the quantum advantage, in the sense, would be showing that if we have actually prepared entangled states of the probes, then we can do better sensing than with separable states, right? Similar to all the rest when you talk about quantum advantage. Good. So this was just a bit small parenthesis. Now, in fact, there are really two very different aspects in which using entangled states can help you sense something. And they're quite easy to understand, the two of them. So first thing is that, we'll come back to this later, is that actually if you prepare an entangled state of your probe, so if you have some initial state of your probes, which is generally quantum, so for example, it exhibits some entanglement, that what can happen is that it will be much more sensitive to small variations of the parameter. Yes. So in other words, if I change the value of the magnetic field a little bit during my evolution, the final state, which will look much more orthogonal to the original state, if I started with entangled state than with product states. This is one thing, right? And this is kind of related to the sensitivity of entangled states. And the other aspect is how much information you can gather whatsoever, right? So, and this is related to the orbit. So, I mean, this is maybe less relevant to the talk, but maybe try to illustrate is, so if I prepare a probe in some state and then I let it evolve, and then what I can look at is the following object is the density matrix, which corresponds to the mixture of all possible final states for all possible values of the parameter. Yes, this is what defines the orbit. That's this raw mean here, right, in the formula. So the average of all possible final states to all possible. Then by Holevo bound, right, you know that this limits the entropy of this object, right? It limits actually the information which I can read out about B, about my parameter at the end. Yes. So this is another thing, but maybe let's not focus on it because. So we'll focus on the first one. Good. So now I'll just quickly show you how the fish information. So actually, how many of you are familiar with fish information, just to have an idea, or at least heard about it? Okay, I see one hand, but I cannot see other hand because, anyway, so not clear. So I'll just now quickly see how you can understand fish information, right? And this, so, right before we had for the classic for the normal fish information, classical, what we had is a curve of probability distributions, right? And then we said that basically the fish information really tells us about how fast these probability distributions become different when we move along the curve. And to say how fast, we can use this fidelity, or which is related to the Hellinger distance, right? Which is this f of PQ. And then, as I mentioned before, the fish information is just basically how fast this fidelity decreases when B changes. Yes. So in fact, now we can have the same thing with quantum states. So now we have a curve in the space of density matrices. And again, if we move along the curve, we can ask the question of how fast now some other distance between quantum states changes when we change B. And it turns out that there is actually one distance, which is precisely the Ullmann fidelity here, right, which I write down here, which when we write, let's consider two states which are nearby, and now let's talk about what is the best possible measurement, right, which minimizes the Hellinger distance between the final probability distributions. It turns out that if we write this, so this, we define now the fidelity between these two states as being the minimal fidelity between probability distributions of the outcomes, then actually you don't need to minimize anything because this is precisely given by this Ullmann fidelity, right, by this trace expression. So in some sense, these two definitions, you can show it that these two definitions are equivalent, this one and this one. So what's nice about it now is that, of course, when we have the distance of quantum states here, what we wanted then is make a measurement, right? And estimate the parameter from the measurement data. But since we have this relation between this relation between a definition with an explicit minimization of all measurements and just this Ullmann fidelity metric, then we don't need to do this minimization, because we can just, we can just go over this thing and say, well, quantum Fisher information now is just given by simply looking at how this fidelity drops when we move along the trajectory of quantum states. You see, so kind of the nice thing here is that a priori you would say, I will just do a minimization of all possible measurements, right, to find which one is the best to extract the parameter. But in fact, I don't need to do this just to estimate the Fisher information, because the Ullmann fidelity formula takes care of this for me. Yes. So we can see, so therefore we can actually define the quantum Fisher information as just the susceptibility of the Ullmann fidelity with respect to B, how fast the states become different when B changes. This is maybe an important slide, so if you have questions, maybe ask them.
Looks clear.
Looks clear, okay. Mm-hmm. Yes, good. So we can also have this geometrical intuition here, right, for quantum Fisher information as a speed of how state moves in this in a space of density matrices, right? Now let's look on some general properties of QFI. Well, I mean, I guess it's not so important, but of course, minimizing the fidelity is maybe not so easy to compute. So instead, what you can do it is actually you can show that the Fisher information, if you solve this as symmetrical logarithmic derivative equation, right? So you have the rho, as we said, you have the state at B, you have the derivative of rho at B. Then if you find the SLD, this operator L, which satisfies this equation, then in fact you get automatically the Fisher information of the state at this point by this formula on the right here, right? By the way, L also is related to the optimal measurement, which you have to do to attain this, but I didn't put it here. Right, another thing is that, again, we can define a quantum angle now, right, as just the arc cos of this fidelity between two states, and actually a quantum angle is a distance, okay? So if you have a whole space of quantum states, then you can define the angle between two states. So for pure states, it's really trivial, just the angle between pure states. For mixed states, it's the arc cos of this fidelity. And the nice thing about it is that it's a distance, and particularly the triangle inequality applies, right? So the distance between like two states like this and like this, the sum of these two distances will always be larger than the sum of the distance, okay? So why is it nice? Because it actually gives you automatically some kind of speed limit. So if you have this curve rho, right? If I have a parametric curve between, let's depend on B, right? So this rho of B here, then I can just integrate the small distance increments along the curve, and I know that actually the states between the first and the last states, they cannot be further away than just the integral of the Fisher information, right? Because the Fisher information is precisely the susceptibility of the angle, right? So this formula holds. And so this is another useful property of it, okay? Now actually what typically people do in experiment is unitary encoding. In other words, so far we just were talking about a general curve in this, in a space of quantum states. But typically this curve is not generated, like it's not just a random one, but it's actually an orbit generated by unitary transformations, you see. So it's really like actually rho B is obtained from some state rho 0 by just acting with a unitary like this, right? So basically you can say it means that we act with an Hamiltonian H for a time B, yes? So of course this simplifies things a lot. And for example, for pure states, then the Fisher information is just the variance of the state with respect to this Hamiltonian appearing here. Okay, I mean, you probably heard about this formula, I don't know. Right, so you can say that how fast the pure state moves under this unitaries is really just dictated by its variance with respect to the generator of the transformation of the Hamiltonian. Now for mixed states, in fact, something similar holds. All right, so a mixed state, you can decompose it, any mixed state, you can decompose it as by mixture of pure states, obviously, right, by definition. Of course, there are different ways to do it, yes? And for each way you decompose the density matrix in pure states, you can get a different average variance. So in other words, for each psi I here, I just compute the variance with respect to H, and then I just sum the average. Okay, then it turns out that actually if I find the decomposition which minimizes this average, then this average variance will precisely give me the fish information, okay? Right? So it's another nice property. So let's maybe just to give you some hint here, let's look on a simple example, the JZ state. So let's consider just n qubit probes. Yeah, so this is our qubit probes here and the collective Hamiltonian. So here the idea is that we have n spins, 1/2, and they're all subject to a magnetic field, which is the same, right? Transverse magnetic field. So then the interaction is governed by this Hamiltonian, which is simply b times h, right? Where each qubit is just rotated with sigma z, yes? So first let's consider an entangled state of all these qubits. So we prepare this GHZ state, which means all spins are up in superposition with all spins down, yes? And let's see what this evolution, where this evolution brings it. Well, it's quite simple because these are both eigenstates of the collective spin, yes, 0 and 1. So simply when we apply this propagator here, well, the 0 n state picks a phase, which is given by its eigenvalue IB times Tn, right? And the 1 state picks the opposite phase, yes? So now if you look on how fast the state moves, depending on B, on the value of B, you see that it's just given by this cosine, right? So, and in particular, if you expand this cosine for small t or for small b differences, then you see that there is a square and this factor n square, yes? So in other words, the variance of the JHZ with respect to the Hamiltonian is quadratic in the number of qubits. Now for a product state, you can do the same computation, and you see that, well, you just get the cosine, the overlap for a single state times n, and then it's just linear in n, right, if you expand it. So this is actually typically known as Heisenberg scaling on the left here for entangled states, where the Fishy information can scale as n square, and standard quantum limit for product states. Yeah. So you see that indeed you can have a very large advantage in the sensitivity in the case of entangled states. Okay, now there's this slide, but maybe I'll skip it because it's a bit technical, but if you have questions about this, we can ask them at the end. Because I think we are running out of time, do we? It's 45 minutes. So just in a few words, you can kind of interpret the Fishy information of a state as a measure of how macroscopic the state is, how quantum macroscopic the state is, right? Because I mean, at least for pure state, I think it's very intuitive. If you have a pure state of some system for which there is an observable whose variance is very large, right? So let's say I have a pure state of my n spins for which the magnetization has a very large variance. It means actually that this property, magnetization, which actually has a very simple classical meaning, right, is kind of indeterminate on a quantum level on a very large scale, right, of the scale of the variance, right? So in other words, we have like a huge quantum fluctuation of this property. Now to go to mixed states, it's a bit more complicated, and I'll skip it. But the Fishy information there is a natural generalization. Yeah, so this is citation of some RMP. Yes, so now kind of we are done with the tutorial, I would say. So let's come back to our original question. And this is the following, right? So we said, we have this general scenario where the probe continuously interacts with the environment, picks up the signal and the noise, and we continuously try to control and read out it in such a way that at the end, when the time of evolution is finished, we want to have the best possible estimate of the signal, this magnetic field B. So how do we think about it? Well, let's make a bold statement. We'll just say that, you know, whatever I do here, the joint state of the probe and my computer, which can be a quantum computer, is just described by this big density matrix rho, which depends only on B and on T, right? Because I fix the sensing protocol. So now from this thing, we want to know, okay, given this thing, how well can I estimate B? So you see already that because it's just, at the end, if I just have this curve of states, this parametric curve in states, I can just use my Fishy information. In particular, even if actually you have some prior knowledge, you can still use some kind of modification of the Cramer-Roo bound, which still tells you that, you know, the variance of the estimator, which will estimate my B, and then it actually can be decomposed in two steps. There is something which depends on the prior here, plus there is the Fishy information, right? Here on the right. So you see, if time is very long, in fact, the prior becomes completely irrelevant because really this thing is dominated by the Fishy information. And so actually how fast the fish information scales with the time here, obviously sets you a limit of how well you can estimate the thing, right, on the left. So this is an important thing here. So in particular, there are actually now two regimes, and I will illustrate them later. So first, there is a diffusive regime somehow, which corresponds to the start of the quantum limit we've seen before, where the interaction of your probe and the environment is such that the fish information of the final state can only scale linearly in time. Yes. So if it scales linearly in time, then the variance of basically the precision of my estimation of the field can only go down as 1/t. Okay. So just from this formula. Now there is also the ballistic regime, where kind of everything builds up in a coherent, like in a constructive interference, and the fish information can scale as t², right? And then it means that in this case, in principle, I could estimate the field with a precision which goes as 1/t². Yes, so we'll kind of, so basically one is this is kind of the classical, the diffusive regime is kind of the classical scaling, where, because of course, if you just repeat the same measurement many times, in fact, you will have like n repetitions, so you will be in this regime, right? This is the usual thing, right? You will have a variance which goes down as 1/n, or 1 time. Whereas in quantum physics, in principle, allows you to attain this one, but not often, in fact. So now I'll give you some examples, which hope will make it clear what I'm talking about. Do you have questions here? No? All right, so let's now take the most simple example possible, just one qubit. So we take one qubit. The Hamiltonian is in the z direction. So basically what we have is we prepare it in a state plus on a Bloch sphere, and then we just let it rotate with respect to this Hamiltonian, right? BH. So, well, you can see the state is, the evolution is just, there is no dot here, by the way. So then again, as the thing is a variance, right? We've seen for a pure state, the fish information is just the variance. So it's just the variance of this thing appearing in the exponential, in the propagator, right? So the B is a parameter. So it's really just the variance of t times h. So obviously the variance of the thing is scaled as t², right? Because t is inside the operator, multiplies the Hamiltonian, right? So this is really describes the final state. So this is an example of the ballistic regime. In other words, you see that, yeah, the state moves away from itself, like as t² in the first order. So it's cosine of t. Right. So the optimal strategy then somehow is, okay, let's just run this interaction forever, and at some point measure the thing and estimate. Of course, this assumes you have a very narrow prior, but good. So this is an example like of pure evolution. There is no noise, so you get this fish information going quadratically with the time. Now let's consider another case where you have actually a different situation. Now I have the same Hamiltonian, so we have this signal which tries to rotate the qubit around the Bloch sphere, but on top of it we have a noise, right, which is just given by dephasing. So then the evolution is described by this master equation. So on the one hand we have this rotation going on the other hand we have this dephasing noise, which tries to dephase the qubit to the center. And there, what happens actually if you solve the master equation? Well, you see that. So first, so the solution now, the fish information is actually this red line here. Right. So first, in the beginning, the noise is still small, so the fish information kind of goes quadratically. But then at some point, the noise kicks in, and then the fish information actually stops growing and goes down to 0. Right. So if you continue to think, it will actually go down to 0. Why? Because the dephasing will make the state go simply to the identity, and then of course the identity state contains no information about the parameter. Yes. So here you actually, if you think about what is the optimal time to measure, well, there is this time which is kind of tangent from the thing, right, where the fish information slope is optimal. Yeah? And clearly here, you cannot go quadratically forever, you can only go linearly, right, with this slope. So if you repeat it again, the best strategy here is, okay, I let it run for this time, which is given by the noise. Then I measure it out. So I measure the state, I learn the parameter, and I repeat the same thing again. So I will go here, here, here. So this is a regime where the fish information can only grow linearly with time, which is a diffusive thing, right? Because there is noise. Now there is another kind of things which is basically very similar, but we just change the evolution, the noise a bit. instead of having a Z noise, the dephasing noise, we now have a noise which is a bit flip noise. Yes. So the noise tries to, so the evolution rotates the qubit like this, and the noise tries to flip the qubit, right, around X. So now if you solve the dynamics here, you see basically the same, similar thing, that the diffusion information tries to go up, but then saturates at some point and eventually will go down to 0. However, actually now this is a tricky thing. This noise is really different in the sense that you can error correct it. Okay, now error correction come in the game, but I hope you can follow it. So consider now the following state, psi 0. So now we have our probe qubit, yes, which is subject to the evolution, which is rotated by this Hamiltonian on which the noise acts. And then we also have our auxiliary qubit, which is kept somehow in our quantum computer, which is used for control. And this auxiliary qubit actually doesn't get any signal, but it also doesn't get any noise. And then we prepare the original state, the initial state of these two qubits in this one, so in an entangled state. Now let's see what happens. You see that if, well, if just the evolution acts, then of course you just get a phase between the two things, right? So you get a phase between these two terms, a relative phase. Now, if the noise acts, then what happens is that the probe qubit will be flipped to an orthogonal state from 0 to 1, right? Because our noise is really just a bit flip noise. And now actually I help you see now what happens, because you see that this state here actually lays in an orthogonal subspace to the original state because it has a different parity. Okay. So this one only has 0, 0 and 1, 1. This one has 1, 0. So in fact, what I can do in principle, if I have quantum control, I can measure the parity of the state without disturbing the phase here, right? So I will just make a non-demolition measurement, in other words, which projects either on a subspace of 0, 0 and 1, 1, or on a subspace of 1, 0 and 0, 1. Yes. So if I do this, I will learn whether there was an error or not. I will learn whether I'm here or not, or here, without destroying the phase, because it projects on a whole subspace, right? So if I do this control very rapidly, then after an elementary error, I could detect it and I could correct it. So what does it tell us? It tells us actually if I come back to the scenario where I have to design an optimal control strategy, then this gives me an active control strategy which will get rid of the noise completely, right? Because by doing this, I will always eliminate all the errors. Whenever an error occurs, I will bring my state back to the no error subspace. Yes. So this is a case where a priori I have a diffusive regime, which is bad for estimation, but with active control, I can actually restore the quadratic scaling. Yes. So this is the examples, right, of things we're talking about. So now we can ask a general question. The general question is, given all this, like, suppose I really now what I have to start with, I'm told that, well, look, this is how your evolution looks like. So your probe, right? This is how the signal acts with some Hamiltonian H, which I know from the physics of my system. Plus there is some noise which is described by, so it's Markovian noise, right? In Liebland form. This is why it comes in the title. And given that I'm only given this, can you tell me now if my scaling, right, if my precision is limited to a diffusive scaling or to a ballistic scaling? Right? So how to do it a priori, right? A priori you can say, okay, well, we just solve the dynamics. So we solve the master equation to get the dynamics. Then we have to look for the best possible initial state, yes, in principle. And then we also have to look for the best possible control strategy. So how to apply these control pulses in the middle. And well, this looks like it's a bit crazy, right? You cannot just do this for everything. But what I can tell you is, in fact, you don't need to do this because you can only check a simple condition. In other words, if the Hamiltonian falls in the subspace which is generated, it's called the noise subspace, which is generated by all of these Limblad operators. Yes, so we just take all the Limblad operators, we define a space, right? And then we see if the Hamiltonian is in there, or there is a part, so with respect to the Ibrichman product, or there is a part of Hamiltonian which is linearly independent to all these guys. And then the answer is very simple, is actually if the Hamiltonian happens to be inside this noise subspace, right, then there is no way to, then you will actually be in a diffusive regime. So your evolution will be such, whatever controls you do, you cannot get information faster than 1/t, right? You can get the precision down faster than 1/t. However, the other result is that if you are actually outside of the subspace, so if there is a component of the evolution which doesn't belong to this subspace, then you will be able to restore isomorphic scaling by active control. Okay, so in some sense now, I would say it's nice because you don't need to solve anything. You just look on this for your problem, right? So for the physical problem you have, the noise you have, and the signal you have, and you can straightforwardly determine whether you will have a quantum advantage in time scaling or not, and whether you can, and if you could have it, how to do optimal control to achieve it. Okay. Now I'll be, I see you like, I'll try to give a sketch of a proof, right, of how this works, but it's a bit technical. So if you found it was already a bit technical before, maybe we can skip it. I don't know. What do you think? Is anybody ready for some more mathematical details? Let's try now. So let's go for it. So now, okay, let's look on the Fisher information of the pure state. Yes. So the pure state, pure state, of course, is just described by this trajectory, right? For unitary encoding. So we get some initial state. We apply this unitary, which depends on B. Okay, and the Fisher information, as we saw, is just given by the variance of the Hamiltonian. Now you can compare this expression to just the naive speed. So the naive speed would be, well, I take psi, I just take its derivative, right? It's just an element of the Hilbert space, and I look at the norm. So this would be kind of the naive geometrical way to quantify how fast my vector moves in the Hilbert space. Yes. In fact, if you do this, you see that, well, actually this guy looks like h squared, so it's bigger than the Fisher information because it's just a second moment. There is no minus h part. Yes. However, you can, okay, sorry. Now at this point, you should recall that the vector in the Hilbert space is not really physically relevant, right? What is relevant is only a ray. So it's basically, there is this global phase invariance, right? So if I give you two vectors in the Hilbert space, which are related by a global phase, they describe the same exactly the same physical state, right? So when I drive a trajectory in the Hilbert space of the states, clearly there is some freedom, some gauge freedom, because for each state psi b, I can attach a global phase which depends on this b, right? So in other words, this thing I write here, this psi tilde of b, is actually described as a curve of the same state. Do you agree with this? Because the only thing which differs here from the previous expression is that I add a global phase which depends on the parameter, but this dependence is irrelevant, right? It's just a gauge freedom to write my state in Hilbert space. All right. Okay. So now I can formally say that, okay, let's look on all possible ways to define this trajectory with all possible psi of b global phases. And then in fact, if you look on now the minimal distance, so the minimal speed of evolution given by this naive expression, just the norm of the derivative with respect to all this global phase dependencies psi, then in fact you get you do get the Fisher information. Yes. So you can say that, okay, basically, the state is described by really the projector on the state plus a global phase, and the global phase is here actually is a gauge freedom. It's completely irrelevant. So it's kind of a parallel transport problem. So I have to find this irrelevant phase which minimizes my distance to get the real physical Fisher information distance. Okay. Now actually the same thing applies to mixed state somehow. Mixed state, you can describe it by this collection of pure states. Yes. But again, there are many different ways to attribute these pure states to a mixed state. Yes. So in other words, this curve of density matrices can be described by a collection of curves in pure states. And again, actually, if I just minimize all possible trajectories of these guys here, I actually get the Fisher information, right? So next step is the same thing applies to quantum channels. So look at what we had before now. What I care about is that I have some evolution. I apply it in initial state, and then I get a final state. And you see the final state given my channel, I can always write it as this object here, which is the sum of Krauss operators applied on my initial states, right? You see this? And again, there is a freedom to choose the Krauss operators, which describe exactly the same channel. So in fact, I mean, you can maybe see it, but in fact, the same exact thing holds here, except that now there is inequality, that the Fisher information of a channel, so for all possible, so for final states first, right, it's actually given by the minimum over all gauge freedoms kind of to define curves in a state of cross operators, right? And then you see here that basically I can just forget the input state, because obviously the expected value of the sum on some state is just bounded by the norm of this, by the maximal eigenvalue of the sum. There is a sum missing here, sorry. So this allows to define the kind of the quantum Fisher information of a channel as just bounded by something which depends on its cross operators, right? And where you can minimize over this gauge freedom of choosing the cross operators the way you like. All right, so that's the idea, right? So take a message for a channel like this, you can just very nicely define the Fisher information which you can attain with this channel by plugging any initial input state as a property of the collection of cross operators which describe this channel, all right? Plus the fact that you have to minimize over all the equivalent ways to describe them with cross operators. Okay, so now next step is, well, you have this global thing, and now we decompose it in infinitesimal steps of very tiny time evolutions, yes, interjected with controls. This is kind of our ultimate control thing we had, right? And then if you look on the global cross operator of this channel, it's just a product of cross operators for all infinitesimal time steps. And then, okay, really, I will just go quickly. So basically what happens when you apply the derivative of this global product on both sides, you have different kind of terms. You have terms where the derivative falls on different times, and these ones you have t square of them, right, or n square. And you have the terms where derivative falls on exactly the same k, and you have t of them. And the goal to play now is by choosing the cross freedom, you want to set the n square terms, the t square terms to 0, okay? And if you can set them to 0, so if you find an Hamiltonian gauge freedom which does it, then basically you show that the t square contribution disappears and you only get a Fisher information which scales as t. And what I didn't show to you is that this happens exactly when the Hamiltonian generating the evolution falls in the subspace generated by the noise operators, okay? So this is, I mean, it's a sketch. So this is how you get this very simple condition, okay? In the same time, you can then, of course, minimize the beta, the bound here you get for the remaining freedoms to get the best possible bound on the Fisher information. Now, for the go part, it's actually similar. If the Hamiltonian happens to be outside of this noise subspace, okay, you find the orthogonal part to it with respect to the Ebridgman product, and you define the error correction strategy. Okay, let's skip it. Maybe now we can go to the interpretation, right? So it's actually, so now we are done with the technical thing. So I'll just tell you how to interpret these results. And here, how I think you should think about it. So first, we have just a general, right? So this is if you talk about how the Fisher information can scale with respect to t in some estimation scenario. Then there are two kind of limits. First, there is a general limit, which is just this quantum speed limit, right? That even for pure states, you cannot go faster than variance of h times t square, yes? So this is a red line, yes? However, now I tell you that on top of it, if you have some noise, then you can also get a linear bound sometimes for some types of noise, actually for most of noises, which gives you like a linear scaling bound, right? Beta times t. So what does it mean now? So it means that actually in the long term, obviously when t is large, well, this blue bound is dominating and it sets really your scaling to just a scaling in linear in time. However, for shorter times, here, it actually just the quantum speed limit. So the general Heisenberg limit, which limits you. So in other words, what you can say here is that whenever you have this noise, you can actually still profit from kind of the quantum advantage, but only up to a certain time. And at this time, you will basically be taken over by this linear bound. So even if, even if you don't have it in general, you have this bound of type beta t, which we just seen previously, it doesn't mean that you cannot have a quantum advantage. It just means that you can only have it for a short time, right? So you can still profit from entangling your probes and so on, but not when time goes to infinity. Good. So now actually we are right on time to the conclusion. So I think there was this kind of two things I wanted to show you that, well, first get some intuition about quantum Fisher information, right? And how it quantifies precision in metrology or in parameter estimation. And the second part is that, well, precisely you can actually get very interesting deep statements about how precision can scale in a scenario just from looking at the master equation with very simple conditions. Yes, and finally, that even if you actually doomed to linear scaling with time, it can still be good in practice to use entanglement and so on. So yeah, this is some bibliography. And that's it, right? So maybe you can ask questions. Hopefully you have some.
Okay, thank you so much for the talk. So any questions, please? So wait a moment.
So I realized it was quite dense, huh? This.
So raise your hand if you have a question.
Кость, меня слышно?
Да.
Кость, меня слышно?
Да, сейчас слышно.
Ну, я написал вопрос в чат.
Я только сейчас увидел, да.
Тяжело говорить.
Have you applied this approach to real experiment?
Да. So one thing we looked at actually is actually not actually my co-authors, not me, but you know when you have a Bose-Einstein condensate, right? And you can squeeze it, and then your magnetic field will just rotate it, and you can have some type of noise like interaction of your atoms. So there, I mean, I don't have a slide here, but yes, it actually quite reasonably predicts what you can get in an experiment like this. As one example. But of course, so for the no-go part, I think it's nice. For the go part, this control is very tough to realize, right? So far, it's not really experimentally relevant. Does it answer the question? Отвечать на вопрос? В общем, да, тут я на теории сконцентрировался больше, но в принципе все это можно достаточно полезно для конкретных систем.
Yes, okay. So any other questions, please?
Можно что-то сказать в случае, если точная модель шума неизвестна? Или нужно обязательно знать точности?
Хороший вопрос. Ну, то есть, наверное, можно сказать, что если ты, например, для всех возможных моделей шума, да, вот это...
Ну, да, худший случай какой-нибудь там, да?
Ну, да, то есть, например, мы можем сказать, что для всех возможных моделей шума, которые нам кажется могут соответствовать нашему эксперименту, вот это условие, например, выполняется, да, то есть, что, то тогда, в общем, понятно, что да, невозможно. Тогда ясно, что как бы не может быть вот этот, короче, quantum scaling of precision. А если ты хочешь с этой стороны это смотреть, да, то есть тогда, конечно, чтобы вот этот протокол, который будет делать error correction, он зависит от модели шума. То есть если ты написал какой-то там такой control strategy для какой-то модели шума, а потом у тебя на самом деле другая, то она не будет работать.
Ну, я это увижу каким образом? Просто вот эта граница будет нарушаться, да?
Ну, эта граница будет нарушаться, да, но и даже, на самом деле, потому что еще, то есть, что вот этот error correction protocol, да, который это делает, давай на английский, error correction protocol, which actually achieves, which removes the noise, really depends on the subspace of the noise, and also depends on the orthogonal component of H. So basically what you're trying to do, you're trying to remove all possible effects on the state which bring you outside of this H parallel. Where is it? So simply, if you're wrong about the subspace, you will not remove the noise, and at the end you will just have a linear scaling. В общем, если ты, у тебя есть... В В общем, если ты там, грубо говоря, что это вот эта стратегия делает, error correction, она удаляет весь шум, который находится в S, и оставляет только все, что происходит ортогонально S. Но если у тебя есть и шум ортогональный S, то ты просто его не удалишь, и в итоге он испортится.
Я не могу получить ошибочно, там, скажем, заниженную оценку или завышенную оценку параметра, ну, точности, да, определения этого параметра, если я пользуюсь неправильной моделью шума. Ну, то есть я вот думаю, что у меня...
Да, элементарно, да, конечно, можешь. То есть, особенно в случаях, когда, например, ты думаешь, что у тебя вот такой шум, и для него там существует такая, значит, стратегия активного подавления ошибок, а оказывается, что еще какая-то другая шума компонента, то,
Ну да, то есть,
весь этот анализ будет неправильный.
Как мне понять-то, потому что как бы я же не знаю истинное значение параметров, поэтому я не могу проверить, действительно у меня там квадратичный скейлинг или линейный, или какой, да, если я истинного значения параметра не знаю. Как мне понять вообще, моя модель шума адекватна или не очень, вот для таких оценок?
Ну, я бы сказал, что на практике, конечно, ты должен знать как немножко физику, да, своей системы, но тут есть, в основном тут вот в чем, если потом приходить уже к применениям этих всех штук, то обычно есть какой-то доминантный шум, да, например, который, например, ты хочешь убрать, но всегда есть еще какие-то шумы, которые, может быть, с меньшей вероятностью происходят, но которые всегда тебя ограничивают к линейной информации Фишера. Но тогда просто ты выбираешь, как бы ты будешь просто убирать доминантный шум, и вот это вот квадратичное время продлишь на какое-то время, да, до тех пор, пока другие шумы не войдут. Но тут важно, как бы, видишь, тут важно не параметры, не скалярные параметры, сейчас, где тут был? Важно не скалярные параметры, которые в этих L попадают, да, то есть не конкретно, например, какая там гамма описывает, да, определенный эффект, а именно операторы, которые его генерят.
Ага.
То есть, если ты немножко...
то есть важно это там диффузировка или...
Да, вот. Если он, типа, если, например, это гамма сигма z, вот это L, да, что, которая диффузировка, и ты не знаешь гамма, то это вообще не важно. Такая же, то есть гамма не релевантна. Вот важно, что это сигма z. Потому что...
Конкретный рейд, да, не очень.
Да, потому что все зависит только как бы от вот этого линейного пространства операторов. Оно вообще не зависит от как бы скаляров, которые здесь попадают. Да. Это такое... Это как бы...
на error correction похоже, на самом деле.
Ну, это есть error correction, да. То есть единственная разница, что как в error correction на самом деле можно все скорректировать, а здесь, оказывается, нельзя все скорректировать. И, собственно, тоже понятно почему, потому что ты не можешь скорректировать саму эволюцию, да, потому что если ты ее скорректируешь, то и сигнала никакого не останется. То есть это такой error correction с условием, что нужно всегда оставлять что-то нетривиальное хотя бы в двумерном пространстве, куда попадает сигнал. Вот, собственно, так можно и понимать эти результаты.
Ну, в error correction, казалось бы, тоже есть логические операторы, которые закодированные слова действуют, иначе как бы вычисления с ним нельзя будет делать, если мы все будем корректировать тоже.
Но там нет ничего неизвестного, там есть эти логические операторы, ты точно знаешь, какой ты хочешь сделать оператор. Тут ты именно хочешь что-то неизвестное закодировать в свою систему.
И можно маленькое замечание, что, конечно же, все это должен быть строго белый шум. Любое, сколь угодно маленькое отклонение от марковости, от дельта коррелированного шума, все разрушит это уравнение master equation, все на свете.
Да, конечно, да. Ну, кстати, я знаю, что мои коллеги там пытались что-то, я работаю над этим, то есть, что будет, если... Но вот эта вся красивая картинка, она, конечно, только для марковости работает. Когда есть какая-то там память уже у шума, все сложнее. Но еще другой очень, кстати, простой случай, это когда шум описывается полностью унитарным взаимодействием, значит, с environment, да? Тогда можно использовать dynamical decoupling. То есть, если мы говорим, что у нас есть какое-то время взаимодействия, значит, системы и окружающей среды, при котором это хорошо описывается все просто унитарным взаимодействием, да? И мы можем делать гораздо быстрее еще какую-то контрольную систему, и тогда еще проще, на самом деле, там все полностью, на все сделать dynamical decoupling, кроме на какое-то направление гамильтониана. В общем, тогда еще легче, на самом деле.
Ну, это когда есть какое-то каноническое преобразование, грубо говоря. Да, есть такие виды шумов. Мы просто возимся с цветным шумом немножко, так сказать, в других задачах, но тоже, так сказать, как влияет цветной шум на все это. Но вот на самом деле можно и цветной шум, но он очень много рушит сразу. Можно последовательно учесть поправки к этому уравнению, что с ним будет, Вот, если учесть конечное время корреляции шума. Вот, это такая некая есть там математика, некая диаграммная техника. Вот, но там уже все много хуже становится.
Понятно. Да, цветной шум — это что-то посередине между dynamical decoupling, да, и...
Да, конечно. Ну, там практически, конечно, там dynamical decoupling в каком-то смысле адиабатика.
Там все сложно, если честно, я никогда не разбирался. Но ясно, что такая простая картина не работает.
Спасибо.
Коллеги, еще вопросы, замечания, пожелания? Предложения, да.
Я даже не знаю, я...
Ну, не знаю, то есть у меня единственный, может, вопрос такой вот, если действительно про экспериментальное применение, то есть вот про базоинференские конденсаты сжатые вы говорили, да, какие-то еще, может быть, применения, ну вот конкретные экспериментальные можно показать, на которых все это хорошо работает.
Ну, как, в принципе, любая система, которая описывается марковым шумом, да, это можно применить.
Ну, вот, что уже работало бы, да.
Ага. Честно сказать, сейчас не знаю, не могу привести пример.
Угу.
Ну, да.
Ну, как бы я больше, мне, конечно, интересовала именно сама фундаментальная задача. Понять, значит, предел.
Это понятно.
Ну, то есть, так вот вопрос, что в любом случае, начиная с какого-то момента, мы все равно упремся в линейный скейлинг, да, то есть поначалу вот этот вот параболический рост будет, да, но потом он, когда в какой-то момент уже с шумом нельзя будет бороться, да, будет линейный.
Если это так, да, если вот это условие не выполняется, то есть если значит, сигнал принадлежит, то есть покрывается вот этим вот шумовым пространством, то всегда в какой-то момент будет линейный скейлинг. Ну и дело в том, что на самом деле как бы на практике, если рассматривать все возможные шумы, то есть на самом деле вот это существует только для, как сказать, лимбладинов, значит, нулевой меры, да, то есть если просто взять случайный какой-то лимбладин, то всегда будет вот этот случай выполняться с вероятностью 1. Как бы, наверное, физическая интуиция такая, что всегда, в принципе, если рассматривать все шумы, которые есть, то всегда мы будем вот в этой ситуации, когда у нас будет в итоге линейный скейлинг, но какие-то доминантные шумы могут быть еще здесь. И тогда мы просто можем их убрать, да, и тем самым продлить вот это баллистическое время, когда мы можем информацию получать от системы быстрее.
Да, понятно.
Можно, я не знаю, может, это какой-то неправильный вообще вопрос. А насколько эти границы достижимы? Ну, то есть мне же нужно как-то еще правильно выбрать состояние, да, вот, и протокол, собственно, вот этой эстимации, в том смысле, что вот этот контроль там, да, и измерение, вот. Это, ну, то есть всегда можно получить эту штуку, да?
Вот, да, хороший вопрос. Значит, вот эта верхняя граница, да, которую мы сейчас, где она? Давай сейчас. Будет график вот этот, наверное. То есть это на самом деле обе достижимы. Вот эта верхняя граница бета-t, если бета действительно, если вот эту задачу решить, то есть все возможные вот эти вот gauge freedom, минимизовать так, что найти минимальную бету, сопоставимую с вот этой, которая здесь появляется, да, то, в принципе, тогда это достижимо только в случае асимптотики, то есть когда много-много, когда t большое. Да? То есть существует тогда какой-то, значит, сейчас как это сказать, я немножко не о том думаю. То есть я думаю, у нас есть гарантия тогда, что мы можем такой fish information иметь, да, при условии, что t большое. Вот. А с другой стороны, вот этот вот error correction scheme, он тоже возможен. То есть, тут еще есть, конечно, загвоздочка в том, что нужно бесконечно быстро применять эти контроли. То есть нужно, как бы тут же все работает, только ты первый порядок шумов можно, значит, стереть. Да, то есть нужно применять эти контроли постоянно на таком уровне, чтобы когда два ивент шума не произошли одновременно. Вот. Ну и, конечно, для этого нужен как бы такой же квантовый компьютер, потому что нужно запутывать постоянно, значит, этот пробы со своим auxiliary qubits. То есть не очень... Но да, это как бы можно сделать в теории. Ответил на вопрос?
Да, спасибо.
Ну, хорошо, вроде как у нас время подходит к концу. Если таких больше вопросов нет, то я предлагаю поблагодарить докладчика. Спасибо большое за интересный доклад. Вот. И да, прошу вас прислать мне презентацию, мы ее там потом тоже вывесим. Вот. Ну, а следующий семинар, там следите за объявлениями, пока свободен. Так что можете предлагать спикеров. Давайте. Всего доброго.
Спасибо за внимание. Я надеюсь, было не очень тяжело.
Местами по-разному, да, но в целом понятно. Спасибо.
Ладно, счастливо. Спасибо.